Swayam Prabha. Digital India. Educated India.
Coming back, now this gamma in itself, gamma in 1 itself can be expanded similarly. So I can have an expression like gamma 10 plus gamma 21 plus gamma in 2 e raised to minus j 2 theta e raised to minus j 2 theta. Okay. Further, in fact, I can now expand this also further. And so on for all the n elements. So if I expand it, it will look something like this. So for all the n elements, if I evaluate this, my value of gamma in as a function of theta will be something like this. Fine. Where these gamma 10 and other values are given like this. Like this. Now I can, so writing it like a series like this, I can write this using the summation symbol. Okay. In fact, instead of writing it like this, I just write simplified. So then okay. Now you see that this is basically a Fourier series. Okay. Now suppose if the theta equal to pi by 2, then implies each T line section is a water wave transformer. Okay. So let us say that theta equal to pi by 2. If uh, if on the other hand, if theta is equal to 0, then my gamma in theta equal to 0 as obtained from this equation, it should be equal to simply, but it should be from this equation. This one should be equal to simply gamma k, that is the simple summation of the mismatch coefficients. But we also know that when theta is equal to 0, that corresponds to f equal to 0, right? So if we go back to our multi-section transformer, what does theta equal to 0 mean? It means that all of these transmission line elements, they have all these, this, all of these have 0 length, 0 electrical length. In other words, this transmission line having characteristic impedance Z0 is directly connected to the load RL. If that is the case, then my input reflection coefficient should simply be, right? But that is not what I am getting, this summation. If I evaluate this summation, then that is not equal to, this is what we should have obtained, but we are not getting that. And the reason we are not getting that is because of that small signal reflection approximation that we have done in deriving this expression. So then, in order to obtain consistent results, we do a little mathematical manipulation. Mathematical manipulations are allowed in engineering as long as the expression obtained using that mathematical manipulation is consistent with experiments. Okay, so the slight mathematical manipulation that we will be doing is like this. Now here gamma k is given by this value, right? So if the mismatch between z of k and z of k is k plus 1 is small, then we can approximate this expression as, so here what we are doing is we are simply considering that the denominator is equal to twice of zk and the numerator remains the same. Now this further can be approximated by another mathematical operation that this is equal to ln 1 plus so what we did here is if we expand this logarithmic series and take only the first term, then that will be equal to this term. Okay. This can further be, so we have done two manipulations. One is, first manipulation is while going from this step to this step, and the second one is while going from this step to this step. Now this is equal to half of ln, sorry, we don't have the 2 here, just have that. So this is simply equal to z of k plus 1 upon z of k. Okay, if this is the value of gamma k that we take, then we obtain a consistent solution, because now if we take the summation of all gamma k's, this summation, then that is equal to half of ln rl upon z0. Here we have assumed that z of n plus 1 is equal to rl, and then this can be brought back to an expression like this using the reverse manipulations. So this we can say is equal to RL minus Z0 upon RL plus Z0, and so then we have a self-consistent solution. Okay. So what this in this part of lecture 11, we have derived this important relationship for the input reflection coefficient of n transmission line segments, each having same electrical length theta connected in cascade. The input reflection coefficient can be given like this, where this gamma k is the mismatch between adjacent sections, and but the thing is, after this derivation, even though we have found out this expression, it doesn't help us much in synthesizing the n sections. What I mean is, what we have done here is that we had started with these n sections, this circuit, and we obtained an expression for this gamma in terms of the Z, in terms of the characteristic impedances and the load impedance. So we obtained an expression for gamma in terms of Z1, Z2 up to Zn and also Rl. But how do we do the reverse procedure? That is, say we are given a gamma in, how do we obtain the values of these Z1, Z2 and Zn? We are given RL also. So we are given what is the gamma in we have to achieve for a given RL. How do we find out the values of these characteristic impedances Z1, Z2 up to Zn? So that is a topic we will be covering in the next part of lecture 11, where we will be starting with some prototype functions. I'll explain what is a prototype function. And these prototype functions are the binomial and the Chebyshev functions. And using these prototype functions, we can obtain the values of these z's, z1, z2 up to zn. Each of the binomial, if I take the binomial prototype function, I will get one set of values for z's, z1, z2, and if I take the Chebyshev prototype function, I will get another set of values for the characteristic impedance. So that we will discuss in the next part. Thank you. Hello, welcome to part 3 of lecture 11. In the previous two parts, we discussed about the theory of small reflections and the analysis of multi-section transformers. So in part 2, we saw how to find the input reflection coefficient of a multi-section transformer. And I also mentioned that what we were doing there was we were analyzing. We were given a certain multi-section transformers with the characteristic impedances of the various sections. What would be the value of the input reflection coefficient? Now in this part, we are going to do the opposite. That is, given a certain input reflection coefficient, how can we find out the values of the characteristic impedances of the various sections of the multi-section transformer? So we are trying to find out the values of the Z1, Z2, Zn uh, of the multi-section transformer. So in order to do this, we take help of what are known as prototype functions. So prototype functions are, they are just functions which have a certain variation with theta, and we will try to, when I say designing the individual sections, what we will try to do is fit the value of gamma in that we obtained in the previous part with these prototype functions. Okay, so it's like a fitting. We will design the z1s, z2 and zns such that the overall value of gamma in match that of the prototype function. So let us discuss what we mean by prototype functions. So let me share my screen. So the first prototype functions, so let me start. So that is what prototype functions are. We will adjust the values of z1, z2 till zn such that the gamma in theta that we obtain matches the prototype function. So let us see. If it is not clear what I meant just now, let me show you by discussing the actual prototype functions. So the first prototype function that we are going to discuss is the maximally flat or binomial. Okay. So the characteristics of this function, prototype function, is that the gamma in theta is such that at theta equal to pi by 2, this is 0. And not only is it 0 for gamma in, it's also 0 at theta equal to pi by 2 for all n minus 1th derivatives of gamma in with respect to theta. What I mean is, okay, so that's why it's called maximally flat. This maximally flat implies that not only the function gamma in at theta equal to pi by 2 is 0, but also all its derivatives till the n minus 1th order are also 0 at theta equal to pi by 2. So let me show you how this function looks like, this maximally flat. So let me share my slides. Are the slides visible? Yes, now they are visible. So this is the way the prototype, the binomial prototype function looks. This red line is the binomial function. Okay, uh, is the binomial function for the first order. What this n value implies, it will become clear in a moment. But before that, so n here implies the order of the transformer. So here the equations that I just wrote were these equations. Okay, that gamma in at theta equal to pi by 2 will be equal to 0. All the derivatives for nth order, for all the n minus 1th derivatives for an n ordered maximally flat transformer will also be 0 at theta equal to pi by 2. And the functions, they look like this. Now what these, the exact algebraic expression for these functions, I'll give in a moment. But notice the flatness that is there at theta equal to pi by 2. Okay, so here it is theta upon pi is 0.5. So this point corresponds to theta equal to pi by 2. The gamma in value is 0. Okay, for all values of n. Okay, and this in turn also implies that the derivative, say for example, if we take the n equal to 4 order binomial transformer, then all its derivatives, that is 1, 2 and 3, first, second and third derivatives will also be 0. The flatness that you see here is the reason the term maximally flat is used. When we discuss the Chebyshev transformer, we will see that this flatness doesn't exist. Instead, there will be ripples. So one way, the advantage of this binomial transfer is this flatness. Flatness is always desired. It doesn't cause variation in amplitude. On the other hand, because of this flatness also, our number of sections, in order to get this advantage of flatness, we might end up needing more sections, which increases the size of the impedance matching network, which, as we shall see in the case of the Chebyshev transformer, by sacrificing flatness, we can reduce the order of the transformer and thereby reduce the number of sections. But that is something we'll see later. Okay, so let's go back. So now the question is, what is the exact algebraic expression of this gamma in? So the exact algebraic expression for this gamma in for an nth order by maximally flat binomial transformer is given by this expression. As you can see, for this transformer at gamma in theta equal to pi by 2, this value becomes 0, and so this becomes equal to 0. Now if I take the derivative, say any kth, or say the first derivative, say, so again what you can see is that this value will be equal to 0 at theta equal to pi by 2, and so this derivative will also be equal to 0 at theta equal to pi by 2. This way you can show that for all n minus 1 derivatives, if you go on finding the derivative of this derivative till the n minus 1th order, all those expressions will be 0 at theta equal to pi by 2, and therefore it satisfies the maximally flat requirement. Also note that irrespective of what the order is, what the value of n is, this will be equal to 0 at theta equal to pi by 2. Okay. Alright then, so now we know what is the expression for the maximally flat transformer. Let us try to find the values of this. Let us see how we can find the value of this n and a. So these are the two unknowns, right? So say we want to match our gamma in as obtained from this equation with our actual transformer, multi-section transformer. So here in this expression, depending on what our bandwidth needs are, two quantities are unknown. One is this capital A and this capital N. So we need to know what is the value of this constant A and what should be the order of the filter. Okay. Now from the graph that I had shown earlier, you can see that as the number of sections, as the order of this filter increases, in other words, as the value of n increases, the bandwidth increases. See this, look at this graph. You see that for n equal to 1, the bandwidth is only this much. Say if we take a point, any value of gamma in, say gamma in equal to 0.1. So when gamma in equal to 0.1, the bandwidth for n equal to 1 is the lowest, and for n equal to 4 is the highest. So from this we can say that as the order of the transformer increases, our bandwidth will also increases. So in other words, if we need a higher bandwidth, we have to have a higher order of the transformer. And as we shall see, a higher order of the transformer will correspond to more number of sections. Alright. So how can we find out the value of this capital A, first of all, this quantity? So to do that, we note that find out what is let me draw the multi-section transformer. So here the characteristic impedance was Z0, Z1. So this diagram I had shown in the previous part.